Hi guys, I'm back with another arcade PCB repair. On the bench today we have a non-working Yia Kung Fu made by Konami in 1983. Another arcade classic. There was actually also a Commodore 64 version, which I fondly remember playing a lot as a kid. Just for fun I started it up on my Commodore to take a look at it again. But we are going to focus, of course, on the arcade game today. I do not have any idea yet what might be the problem with this PCB. I got it as non-working, as always. And also, as always, we are going to go through the troubleshooting and repair process together step by step, so that this video might help you with your own arcade PCB repair. So let's get it on. Okay, so first of all, the PCB appears to be complete. That is always good. Also, there's no signs of any previous work having been done to this PCB. You know, all the solder connections of the components seem to be original and in good shape. So nobody has fiddled around with this PCB so far. It's actually pretty dirty. I will have to clean it at some point. I already hooked it up to my test setup here, so let's just take a look what it does. Okay, so this is what we would call garbage on the screen, right? So there's no real signs of a running game, even though there is some graphics on the screen, and we also have some repetitive noise here coming from the game. Yeah, and also the screen is like intermittently flickering. I don't know if this is a sync issue maybe. We'll have to look into that. But yeah, I think the first step for garbage on the screen, we've done this many times before, would be to actually probe the CPU and see if the CPU is running. And the CPU in this case is this guy over here, and this is a 6809 Motorola microprocessor. Okay, so I hooked up the logic probe and I found a pinout of the microprocessor on the web of the 6809. This is the version E of the processor that is used in this case. E meaning that it has a pin configuration for use with an external clock. Well, we can start with power, for instance. The CPU will need power, so 5 volts is VCC, pin 7, and ground should be this BSS at pin 1. So pin 1, let's check, pin 1 should be ground. That is the case, and 2, 3, 4, 5, 6, 7. We have 5 volts here. That is good. Okay, so next thing we need to run is a clock signal, of course, and in this case this would be those inputs here, Q and E. So that would be pin 35 and 34. So we can check those. 40, 39, 38, 37, 36, 35. This would be one of the clock pins. It was this would be the other one. So they are having a pulsing signal, which is okay. So next thing we can look at is the reset signal. It needs a steady high input on the reset pin to actually run the game. So that's 37, 4987. Oh, interesting. We have a pulsing signal on reset. Okay, and this might actually explain this sync issue, because I don't know if you can kind of see it. It's difficult to show, but there's kind of a synchrony with the pulsing of the reset line and the flickering of the screen. So this indicates to me that this is actually some kind of watchdog that is going off on this PCB. There's some kind of mechanism on the board that is trying to reset the game over and over, because it's detecting, so to say, that the game isn't working correctly. I think this will be the reason for the reset signal to show this slow pulsing characteristic. Very interesting. Okay, I was just continuing to probe the CPU. I noticed that, it is not really running. If you look at the data lines, this is, for instance, data bit 7, data bit 6. This is low all the time, this is high all the time. Data bit 5, data bit 4, and so on. They are not really, they are sitting there at some random state, but they are not really wiggling, they are not really doing anything. And the address lines of the CPU, they are not, they are not even connected. They are high impedance. They are not doing any, they are not there actually. So this CPU isn't running at all. I think the pulsing reset signal shouldn't be the reason for that, because this is resetting maybe twice every second or so. In between, there's lots of time for the CPU to do stuff. So, and it is doing nothing at all. So that is very peculiar. Okay, one thing that can actually prevent the CPU from doing its job is if it is maybe interrupted or halted by an external signal. So we should actually look at lines 40, which is a halt signal, and also 2, 3, 4 on the CPU, because those are the interrupts. If they are pulled low, they will probably be able, those lines will be maybe able to at least prevent the CPU from doing what it normally wants to do. So let's just check those lines, what their signal status is. So the interrupts are 2, 3, and 4. We have a high signal on the NMI. We have a high signal on the IRQ. And we have a high signal also on the FIRQ. So the interrupts are all not active, and this would be the halt signal. This is line 40. This is also high, so this is not the reason also why the CPU isn't doing anything. What does the busy signal say? It's the 33, 40, 39, 8, 7, 6, 5, 4, 3. Busy signal. It's also disconnected. It's not connected to anything. Okay, so this is indeed very peculiar. I don't know. I think additionally we should look at the schematics of the PCB, which I already found on the web, to see what pins of the CPU are actually connected to the circuit on the board, because there are some other inputs or outputs I'm not really familiar with. But you know, as it looks at the moment, what might be the case is that actually the CPU is bad, because I think it should be doing more than nothing at the moment. It has power, it has clock, it has reset, intermittent, high. It has no interrupt lines which are pulled low. It has no halt signal. It should be doing something. It should at least be having some, you know, wiggling address and data lines or so. That's very interesting. So maybe this guy is not working right. But well, for maybe some additional aspects, let's look at the schematics of the game. Okay, and this is the schematics of the game, all neatly put onto one page actually. Turns out the CPU is up here. This is the CPU right here. And well, as it looks, we actually already checked all the lines that are, according to the schematics, connected to the CPU. We checked the interrupt lines, pins 2 to 4. We checked the halt signal. We checked the reset. We checked power. We checked E and Q, which are the clock. And well, there's not much more left, you know, the address, the data lines. We didn't look at the read-write signal, which is pin 32. We could actually additionally do that. So 49.876.542 is also high impedance, doing nothing. That's also a bad sign. Well, CPU seems to be bad, you know. Well, one final thing we could do is actually look at the maybe look at the clock signal with the oscilloscope, if there's something wrong with the clock signal. Yeah, maybe let's just do that. Okay, so probing the pins E and Q, we can see that there's actually a very good clock signal indeed. So these are the two signals, E and Q. They are 1.5 megahertz signals, which is the processor's working speed, and those signals have a height of 5 volts both, and they are, you know, slightly offset to another, which is how it is supposed to work. To get the CPU running, so the clock signals aren't the problem. We could also look at the reset line with the oscilloscope, I think, which was line 37. So we would move over 2 positions here, and okay, so here we see the reset signal. The reset signal is generally high with some short interruptions where it's being pulled low by the watchdog, obviously. Okay, so yeah, so the game is being reset at a frequency of 3 Hertz, so 3 times every second this game is getting a reset. So which is probably the regular function of the watchdog. So well, I think, well, I already well, I forgot to mention, I already did look at the CPU and the socket, and I reseated the CPU, and the socket and the CPU legs are okay, no signs of corrosion or anything. With this kind of socket you can easily check the signal at the socket level and also at the CPU leg here. So you can see that there's actually a good contact probably on all pins. So I think we can rule a connection problem out, which would also be possible, of course. So that leaves us with a dead CPU. So as it looks, I will have to get a new replacement CPU for this board, and then we will continue from there. Okay guys, so a bit of time has passed, and I actually did wash and clean the board, and also I received replacement CPUs for the game, actually a stack of 10 6809 CPUs that I ordered from China, and they were unbelievably cheap. You know, those 10 6809s actually cost me about $5 including shipping. And I already put one of them into the board. And the bad news is that the board still doesn't run, and actually there is the same problem like with the IC, the CPU that was initially in the PCB, that there's no signals whatsoever on the address and data line. So yeah, I was actually in a bit of a dead end here with this repair. And I was always thinking, did I miss something? Is this really a CPU problem? Might there be any other circumferential problem that might be causing the CPU to stop or to hold? I really couldn't figure it out, and I was about to release this video as a sort of an unsolved repair, but then I actually got back to the seller of these ICs, and I noticed that some buyers actually left some really bad reviews stating that these ICs were actually some, yeah, you know, like reproductions or fakes, and that they weren't working for them or partially not working for them. So I ended up testing all of these ICs, and all of them do not work. But having lost trust into the Chinaman, I actually, you know, bought another Motorola 6809, and I think this is really an original, legit Motorola IC that I got here. This IC cost 3 times the money that those 10 ICs cost me, so it was a bit more expensive, about $15 or so. Yeah, but the good news is this IC, this CPU actually does something. So if you put it in a PCB, you do get some wiggling data and address lines. The bad news is the game still isn't running, but I'll show you in a minute. But at least we got our basic CPU circuit signals back, so we can continue on with our repair. Okay, so with the CPU in place, we see that there's actually, these over here are data lines, that there's actually wiggling signals everywhere now. And also, you know, the address lines which were floating before, they are doing something. So the CPU is actually kind of doing its job, so that's good. But unfortunately there still seems to be another problem with the PCB, because as you can see, the game isn't running still at all, and we actually resolved the problem in, you know, in the center of the process, which was the CPU itself. But you know, to basically run, you already know that from previous repairs, we don't only need the CPU. The CPU needs to have access to ROM chips where the program code is located on, and it will probably need access to RAM chips to be able to work. These ICs, the ROMs and the RAMs, are usually connected through several logic ICs which do control the bus and which do some decoding for the chip select, etc. So these are now should be closer inspected by us. Okay, so looking at the schematics, we do have the main CPU over here. We checked all the signals already, they were okay. The main CPU is now running. It is connected through several buffer chips on the address and data lines to those two ICs here, which are at position 10D and 8D. These are EEPROM chips 27128, and these are probably containing the program code for the CPU. They are really directly connected to the CPU address and data lines. We do have two RAM chips over here that are also really directly connected to the CPU, which should be the main CPU's working RAM. Two ICs at position 12F and 13F of the type 2009. I'm not really familiar with this kind of RAM chip, but you can actually see that on the schematics that it is a RAM chip because it has address lines, data lines, chip select output enable like an EEPROM chip, but it also has this line here, which is the write enable. So this actually makes the difference between RAM and ROM chip, a RAM chip, because you will be able to write data into the RAM, needs a signal line to tell the RAM whether it should read or write. So we do have those two RAM chips here. They also have buffer chips to connect them to the data bus. And also up here we have a bit of logic going on, which is mainly the decoding logic for the chip selects for those EEPROMs and RAM chips. And what that means is that judging by the setting of the address lines, a special IC of those EEPROMs and RAMs will have to be selected. Each IC has its own address. Those logic chips are decoding this address, and they are actually then outputting chip select signals, which then activate the chip that is being addressed. So this, what we see on this page, is actually under suspicion. The schematics are actually quite larger, and there's lots more stuff going on, but this is really, the central element of where the game is running. So looking at the screen and seeing that there's still nothing going on, that there's no problem really, basic program really running, I think this is the area which would be of interest now. So looking at the PCB, we do have the main CPU here, we know that already. We do have the program ROMs over here next to the CPU. These are the buffer chips for the address lines. I think this is the buffer chip for the data lines, for instance. And the two RAM chips that the main CPU is talking to are those two guys down here. And they also have their buffer chips. And this is, the area of interest here on the PCB layout. Okay, but how do we actually now go about, finding the fault in this remaining circuit? One way you could actually do it is using this tool over here, which I used in a couple of repairs I did before. This is the Fluke 9010, which is actually a dedicated microprocessor circuit troubleshooting and debugging device. How it works is that you connect this device actually to the CPU socket, And through this device, you can then actually test the circuit on the PCB, and you can test the access to the buses, and you can test the contents of the ROMs, you can test the RAMs, if you can read and write from the RAMs, and you can also debug problems with the with the decoding a circuit, or with the chip selects, or the other ICs, input signals regarding write, enable, output enable, etc., etc. Very comfortable way of troubleshooting a non-working microprocessor controlled circuit. But unfortunately today we can't use the fluke, because for the fluke you need like a dedicated connector, a dedicated pot for every single type of processor that you want to troubleshoot. And unfortunately for the 6809 I don't have the fluke pot, so we are actually we will have to go back to basics, so to say. And I don't think that this is too bad, because previously some of you said, okay, please in the upcoming repairs use the fluke, show us how the fluke works, and they had great enthusiasm for this device, which I can understand. But in the last repairs that I did with the fluke, there were some people saying, okay, so you fix this very complicated problem using the fluke, but I don't have a fluke, so how would I have been able to do the repair? And that is a legitimate question. So most of you will probably not have the fluke ready to troubleshoot your non-working arcade PCBs. So we will have to go back to basics with this repair. And we will just start with this, our trusty logic probe, and get into probing right now. Okay, the first thing I just did is I looked at the ICs that connect the CPU to the address bus and the data bus. And these are buffer chips, these 20-pin ICs. And we have two of them here and one of them here. And I checked the signal lines of those buffer chips, and all of them are actually wiggling on both sides of the ICs. There's activity going on, so at the first glance I don't think that there's any problem with those buffer chips connecting the CPU to the address and data lines of the general circuit. Okay, so the next thing I would look at now is the EEPROM chips with the program code on them. They should actually have lots of toggling signals, basically on all the address and data lines, and probably also on the output enable line. These are the relevant pin connections for those EEPROMs. And looking at, I think these are address lines here, so the EEPROM chips are being addressed, and they're also, I think about here, we should have the data lines. They are also sending out data, probably. Another important thing would be to look at, the output enable for both EEPROMs. This is how they are actually switched on and off, depending if the CPU actually wants to talk to them or wants to talk to somebody else. So these are at pin 22. So I think these are 28 pin ICs. So this is 28, 27, 26, 25, 24, 23, 22. So this is over here. This is a toggling signal for this guy and also for this guy. So judging by the signal lines, there's no obvious problem with the EEPROM chips. And what I also did regarding the EEPROMs, I removed them from the PCB and put them in my trusty EEPROM reader and confirmed that they're actually containing the right content for this game, so that they are containing the actual program. You do this by reading the data on the chips onto your PC or Mac and then comparing them to the MAME database. And if you're able to find the content of your ICs here, which I was, in the MAME database, then you can be sure that the code that is on the EEPROM chips is actually correct, and the CPU should be probably able to run the program with those EEPROMs in place. Okay, the next thing that I did is I looked at the main CPU's RAM chips, which are over here, and again I found toggling signals on the address and data lines. Also the chip selects are working, but there is one thing which is very suspicious, and that would be the write enable signal, which is where do we have it? Right here, which is pin 21. If we look at pin 21, I think that is a 24 pin IC. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So this 3, 2, 1. This would be pin 21 on this RAM chip, which is a toggling signal. That is okay, but on this RAM chip we have right here. What is this? So this is not toggling, and also this is not really a high signal, but it appears to be a floating signal. It's when I touch it with the probe, I get a very short flash, that you could think, okay, that's a high signal, but it's actually not, because as you can see, the probe's light intensity when I'm touching the pin is actually as bright as when I'm touching nothing at all. So a high signal would look like this, of course. The signal this probe would get brighter if I touch a high signal, but in this case it's a floating signal. So if the write enable input to this RAM is floating, means that it's connected to nothing, then this RAM chip probably can't be written and read correctly, of course, because it can't toggle between read and write. And therefore, even if the RAM chip would be working all right, it wouldn't be working for the CPU in the way that it is supposed to be. So next we would have to find out how it comes that this signal is floating. Maybe there's some bad connection, or there's some trace on the CPU damaged, or well, I don't know. Let's check the circuit where the signal is supposed to come from. Okay, looking at this circuit, you can easily see that this is coming from a logic gate. This is the this RAM chip is the RAM chip in question. This other guy has the working write enable signal. His signal is coming from a logic gate at 15A. It's an LS32. And the problematic one is coming from another logic gate LS32, which that should be an OR gate actually, I think, as it looks here. So okay, the inputs to LS32 are read-write. This is the signal that is coming from the CPU, and one other signal, yeah, which probably has to do with selecting the chip. Okay, so let's look at the LS32 at 9E, look at the pins 1 to 3 and see what we get. I just looked up the data sheet for the LS32, and yeah, it's a quadruple 2-input positive OR gate. In our schematics we have the inputs at 1 and 2 and the output is at 3, and there's 3 other OR gates on the IC. So let's take a look what they do. This is the IC in question. It's at position 9E as it looks. Yeah, that's right. So we are looking at pin 1, which is the first input to the OR gate. So this is a toggling signal. Second pin is permanently high at the moment. And this is the second input, and this is the output. Yeah, and it's also floating. Yeah, it's floating all right. So this OR gate should be bad. We can actually look at the other gates as well. We should have another input here, toggling signal, high signal, output is low and a bit flickering, very interesting. So if you have an intermittent signal and one signal which is permanently high, the result of the OR gate should actually be a permanently high signal because of this input here, which is already enough, you know, to let the OR gate output a permanently high signal here, but actually it doesn't. This is low, and yeah, maybe also floating or something. So this IC is definitely bad. So I think we have found a real problem with the circuit, yeah, which is in the end, you know, preventing this RAM IC from running correctly. And as there's also other you know, logic gates in this IC, probably some other functions on the board are also no, sorry, this IC over here are also, you know, compromised. So yeah, let's I would suggest I remove this IC, I put a socket in, and we put in a new LS32 and check how far we get from there. Okay, I did replace the LS32, I did put a socket in. Unfortunately I lifted a bit of a trace here, but not too much of a problem, could be easily repaired. So I hope the signals from this OR gate are now back to the circuit, and the new CPU is in place, of course. So let's fire the game up and see how we do. Oh, still, no, it's doing something. Oh, it said RAM, ROM, okay. And we are, yeah, the game is running, isn't it? Oh, nice. Oh, really cool. It looks actually pretty similar to the C64 version, doesn't it? Okay, great. So let's just try to coin it up. The sound is connected, so we don't have any sound. Oh, we do. This is the coin up. Okay, so let's... Oh, great. to work. Yeah, cool. Controls seem to work also. It's a bit hard to fight and film at the same time, okay? But I'll try that out in detail later. But yeah, I think everything's fine. So the PCB is working again. So great success. Thank you very much for watching, I would say. So this time we were able to fix the PCB with just the basic means and a bit of patience. And yeah, I actually had to overcome those ICs. You know, I really was about to stop this repair, but of course I'm glad I didn't. So beware of those fake ICs, one of the key messages from this repair. If you have any questions regarding this repair or your own repairs, please feel free to post them in the comments below. I'm really answering each and every question that I find on my video comment sections. And well, I would be happy if you would subscribe to my channel if you liked the video. There's plenty more videos. And yeah, I would say thank you very much again, and see you in the next repair.